Okay, so now we move to the last part of this lesson in simple harmonic motion. We are going to discuss about vertical oscillation. Okay, so we are going to discuss about vertical oscillation. So there are many rules when it comes to the vertical oscillation. So we will go through these rules one by one as we discuss the questions. Okay, so first we'll go through the questions and I will give you the required rules that you need to know in each section. Okay, right. So let's go through the questions. Question number 1. Whenever a numerical value of g is required, take g equal 9.8. So you know this rule. Okay, a particle P of mass 0.75 kilogram is hanging in equilibrium attached to one end of a light elastic spring of natural length 1.5. So guys, do you see the difference in this question and the previous one? The previous section we were dealing with horizontal springs, but now the strings are and springs that we're using, they are vertical, they're hanging in equilibrium. Now they say here a particle 0.75 kilogram in mass is hanging in equilibrium attached to one end of a light elastic spring of natural length 1.5 meter and modulus of velocity 80 Newton. The other end of the spring is attached to fixed point A vertically above P. Now in part A, they're asking you calculate the length of the spring. So guys, how do you calculate the length of the spring? So what do we do? Shall we first, let's draw a series of diagrams. Okay, so let's draw the series of diagram. In the first one, we have the spring. The spring has a natural length of, how much? 1.5 meter. Okay. And then what are we doing? We attach this particle of mass 0.75 kg. So what happens when you attach the mass of 0.75 kg? You know the spring will stretch. Guys, do you agree? The spring will stretch. It will stretch a little bit beyond its natural length. Do you agree? So draw a series of diagrams. This is what you should do in M3. So natural length is 1.5 meters. Guys, do you agree? Okay, and then, so I'll mark this length as E. E is the length, basically the string is naturally extending, the natural extension because of the weight of the particle. Okay, so due to the weight of the particle, this will slightly displace, isn't it? The string will slightly displace. So I will name that natural displacement, the amount the string is stretching because of the weight. So we'll name it as E. Okay, so shall we mark all the forces? Now you know this particle is in equilibrium at this point, right? Guys, do you agree? Now when you attach the particle to the spring, it will extend a little bit down and the particle will now be in equilibrium at this particular point. Okay, so what I want to do is now they're asking you in part A to calculate the length of the spring. What's the length of the spring here? The length of the spring is this L plus this E. So you have to find the value of E. How do we find the value of E? So you know at this point the particle is in equilibrium. It's in equilibrium means forces are in balance, right? So what are the forces we have here? You have the weight mg 0.75 g, and you have the on top you have, since it's a spring, you have tension. These are the only two forces you have here, right? So since the particle is in equilibrium, the tension must be equal to 0.75 g. Guys, do you agree? The tension must be equal to 0.75 g to be in equilibrium. So tension is lambda x over L is equal to 0.75 g. Guys, can you substitute the value? Lambda is, do we know the lambda value? Yeah, the modulus of elasticity is given to us as 80 Newton. So lambda is 80 into what is the x value? E. What's the natural length? Natural length is 1.5 equals 0.75 g. Guys, do you agree? 80 E over 1.5 equals 0.75 g. And then you can now make E the subject. E is 0.75 g into 1.5 divide by 80, right? 0.75 g into 1.5 divided by 8. Shall we type this in the cal? Let's get the answer. So we get E equals, the fraction value. Now we remember G is used as 9.8. So the fraction value 441 over 3,200. But you know there's a rule normally when you use G as 9.8, we leave answers to 2SF or 3SF. Okay, so then you can take a few. This is not the final answer, so I'll take a few extra decimals at this point, 0.1378. So they asked me us to calculate the length of the spring. So what's the length of the spring? Length of spring is the natural length plus the extension. So what was our natural length? 1.5 plus 0.1378. And then that answer you can give it to 3SF. So when you add it to 1.5, you get 1.6378 goes on. So when you correct to 3SF, we get here 1.64 meters correct to 3 significant figures. So that's the answer correct to 3SF. Okay, so this is the answer correct to 3SF. Okay, so we'll move on to part B. Okay, so then let's move to the next part. Okay, we calculate the total length of the spring. Part B, they say the particle is pulled downwards and held at a point B, which is vertically below A. The particle is then released from rest. Show that P moves with simple harmonic motion. Okay, now listen to this really carefully. Now, I have told you previously when we were working with horizontal SHM, whatever the place the particle is in equilibrium is what? Whatever the place where the particle stays in equilibrium becomes what? Becomes the center of the simple harmonic motion. Now you can see your particle is in equilibrium at this point, right? With this extension, with the natural extension, with the wave, the particle is in equilibrium here, which means this point that we marked over here, this is the center. And whatever the amount that you displace your particle from the center, now from the center, the initial amount you displace. From the center, the initial amount that you displace will actually become what? Will become the amplitude of your simple harmonic motion. Now, are they telling you how much of a distance they are pulling downwards from this equilibrium position? They have said that the top point is A, right? The particle is then pulled downwards and held at a point B, which is vertically below A. A is at the top. The particle is then released from rest. Guys, you can see they are not telling you how much they are pulling, which means do we know the amplitude? No. Remember, if they gave you that they pull the distance, if they gave you the distance clearly, then that becomes the amplitude. But over here, they're not telling you. Okay. Anyway, they're asking you to show that P moves with SHM. Okay. How do we prove an object moves with SHM? The rules are very simple. You have to apply F equal MA at a general point and prove that the characteristic acceleration equation looks like x double dot equals minus omega square x. Okay, so let's draw another diagram. So I will mark all these important positions. This is the natural length. This is the center of the SHM. This is the center of the SHM. And I'll mark the amplitude over here, somewhere over here. Okay, so I'll mark the amplitude. So what we'll do here is we'll consider the particle at a general point. Guys, are you with me? I'm considering the particle at a general point. Can you see I have taken this point as amplitude? Okay, that's the lowest point. Whatever the distance that you pull from the center, the lowest point you pull becomes the amplitude. So we don't know that. But you know the rule, if you want to prove the object moves in SHM, you have to consider the particle at a general point. Are you with me? So this is a general point because this is the center, right? Guys, this is the center of your SHM. Are you with me? Let me mark everything. This over here, this is the center of the SHM. Are you with me? So whenever, whatever you are moving from the center, away from the center, you measure X. Can you see? The displacement, the SH, in the SHM, you measure it away from the center. Do you agree? This length was the natural length, 1.5 meter. This length was the natural extension, E. Are you with me? So this length is X. Now this particle is in motion. And this is a general point. Okay, the lowest point is the amplitude. This is the center. So I have to consider the particle at a general point. It's moving. Okay, so shall we mark all the forces acting at this particular point? What are the forces acting at this particular point? Now this is a vertical system. What are the forces acting here? You have the, definitely now you need to consider the weight. You can remember in horizontal, did we consider the weight? No. But now in vertical, we consider the weight as one factor. So what is the weight here? Have they given us the mass? Mass is 0.75 kilograms. So weight will be 0.75 G. And now you have tension acting upwards. In this case, are the tension and the weight going to be equal? When you are in movement, when you have pulled this and when it's moving, are the tension and the weight component and weight, are they going to be equal? No, the tension and weight are equal only at the equilibrium position. Okay, so over here the particle is moving. It's moving in simple harmonic motion. So what's the rule that we do here? I have told you, you must use what? F equal ma away from the center, because towards the center it's negative, away from the center is positive. So you can see in this case, away from the center, I'm using downward direction as positive. Are you with me? So what are the forces? 0.75 G minus tension. 0.75 G minus tension equal mass. Mass is 0.75 into X double dot. Guys, do you agree? Okay, before we start on this, shall we get the tension? What's the tension at this point? Tension is lambda X over L. Lambda value is 80. Guys, what about the extension? I have told you now several times, the X here doesn't mean the X that you have as the displacement away from the center of the section. The X here represents how much your spring has stretched beyond its natural length. So can I know how much the string has stretched beyond the natural length at this point? How much has the spring stretched beyond this natural length? It's this E plus this X. Can you see E plus X? This is the distance the string has stretched beyond the natural length. So the extension is E plus X. This is clear. Divide by natural length is how much? 1.5. So let's input the values. 0.75 G minus tension is 80 into E plus X over 1.5 equals 0.75 X double dot. Are you with me? Okay, so now you know we need to try to prove the characteristic simple harmonic motion equation. Shall I expand the bracket here with 80 over 1.5? So I'll take 80 over 1.5 as one term and expand this bracket with 80 over 1.5. So what do we get here? 80E over 1.5 minus 80X over 1.5 equals 0.75 X double dot. Guys, are you with me? Are you with me? So now, if you try to use, now you can see you have to input the E value which we found previously, right? So if you go to input the E value which you found corrected to the decimal places, you will not actually, be able to get this properly. So either if you substitute the E value, use the full substitution. Or else you could use a small shortcut here. Guys, do you see this? Guys, look at this very carefully. Do you see this? 80E over 1.5 is actually equal to what? 80E over 1.5 is actually equal to 0.75 G. Guys, can you see that we have 80E over 1.5 here as well? Do you see? Okay, so you could do a direct substitution in this manner, or else if you are going for E, you could make sure you use the full value of it. Otherwise, you won't be able to cut the constant. Okay, so over here, I'll directly go with this 0.75 G. Guys, this becomes what? The other term also becomes minus the other term 80E over 1.5 is also 0.75 G minus 80x over 1.5 equals 0.75 x double dot. So we'll cut off, I think you can see 0.75 G, 0.75 G cancels out. So we get here minus 80x over 1.5 equals 0.75 x double dot. So we get here minus 80 x divided by 1.5 into 0.75 equals x double dot. So we get here minus 640 over 9. Minus 640 over 9 equals to x double dot. Can you see? So this is the characteristic equation. Therefore, P, the particle moves in simple harmonic motion. Is this clear? Okay, so we'll move to the next part. Okay, so we just showed that P moves with SHM. They are asking you to calculate the period of the oscillation. How do you calculate the period of the oscillation? So how do you calculate the period? Part C. How do you calculate the period of the oscillation? Period equals 2 pi over omega. Guys, we know the omega square here, right? X double dot equal omega square x. Omega square was 640 over 9, isn't it? So shall we input the value? Guys, can you tell me the simplified answer? 2 pi over omega. 2 pi over omega is root 640 over 9. Shall we give this value without typing pi in the calculator? In that case, you will be able to get an exact answer. If without typing pi, you give in the cal 2 over root 640 divided by 3. And then we'll input the pi from we'll write it down. Then you get, what do we get? 3 root 10 over 40. Can you see? You get 3 root 10 over 40 and you write the pi. Okay, sorry, 640 over 9 here, right? This is 2 pi over root 640 over 9. Okay, so if you type this thing in the cal without giving the pi, you will get 3 root 10 over 40 and make sure you input the pi. Is this clear? So that's the period. Okay, so this is the period. All right, and then let's go to the next part. Can I also have this period to 3SF? Point 745. 0.74509411. So 0.745 to 3SF. Is this clear? 0.745 seconds. Okay. Let's move to part B. The particle passes through its equilibrium position with speed 2.5. Guys, what do you know about the speed at the equilibrium position? You know the equilibrium position is the center of the SHM. The equilibrium position, remember the equilibrium position that we have over here is the center of our SHM, and the speed with which we pass the center of the SHM is also the V max. So maximum V max is 2.5. They are asking you to calculate the amplitude. So what happens? In part D, you write V max is 2.5 meters per second, and you know V max occurs when x is 0. So we can apply V square equal omega square a square minus x square. So V square, that's 2.5 square. Omega square was 640 over 9. Amplitude is a constant. We don't know that. We have to find it. Minus x is 0 at this point. So 2.5 square into 9 divided by 640 equals to a square. So 2.5 square into 9 divided by 640 whole thing square root gives the amplitude. So get the positive value. 3 root 10 divided by and then how much is it to 3SF? So 3SF answer is 0.296 meters corrected to 3SF. Okay, so this is the answer for the first question. So this is the start of vertical simple harmonic motion. There's more theory into this. So this is just the first question, but there are more theories that comes in this lesson. So we will go through them with the next few questions.